Hello everyone, and welcome to our webinar All-in-One Bluetooth Audio, a complete solution on a TSMC 12 nanometer single die. Thank you for joining us today. Over the next few minutes, we will walk you through the technology, the market drivers, and the architectural choices behind next-generation Bluetooth audio solutions. So I am Franz Dugan, Senior Director of the Wireless IoT Business Unit at Ceva. Joining me today is Etienne.
Hi everyone, I'm very happy to be with you today. My name is Etienne Cachet. I'm the Audio Product Line Portfolio Manager at Dolphin Semiconductor.
Thanks, Etienne. We are excited to discuss how Ceva and Dolphin are enabling a new generation of highly integrated Bluetooth audio SoCs. Before we start, a few logistics. So please fill out the survey at the top of your screen. It's very important to us. And at the end of this webinar, we will have a live Q&A session. So feel free to submit your questions at any time during the webinar using the Q&A box on the right. On the left, you'll find useful resources and our contact details. So let's dive in. So in this webinar, our objective is to give you a clear understanding of the challenges faced by modern audio peripherals, especially the TWS and OTC hearing devices. We'll review the trade-offs of existing design approaches and explain how the joint Ceva and Dolphin solution addresses power, integration, and performance challenges.
In 2026, the TWS market is considered to be a mature market. The customers know what they are looking for, and the OEMs are pushing for new use cases that are different from just call and sound. They want to differentiate from competition and add new things to the devices. A change period in 2022 when the US and global regulation allowed over-the-counter hearing devices, meaning that device maker could add plus 35 dB of amplification and entering the hearing devices market. It has been used by Apple in fall 2024 with the earbuds product, where they updated and add hearing test and sound personalization. There is a strong adoption in this market. The TWS is 300 million units per year. There is the rise of open wireless stereo, meaning that the speaker is not inside of the ear but next to it, so it's open ear product. There is a rising demand for smart glasses with a lot of new players. We know, for example, Meta Ray-Ban, EssilorLuxottica with a CAGR of 27.3%. You have below different use cases and different products, such as the Jabra Enhanced Select 300, which has a similar form factor than a true hearing aid, but it's actually over the counter, meaning that you don't need medical prescription to buy it. The Apple AirPods Pro we talked about with hearing test and age feature. The Nuance programmable hearing assist with open ear speaker, so glasses with audio, but also the Meta Ray-Ban smart glasses that are more aiming to replace smartphones by having a display inside.
So what are the TWS challenges? Designing a TWS device is extremely challenging. You must deliver long battery life in a tiny form factor to maximize the user experience. You need to support advanced audio features like spatial audio, ANC, and transparency with high fidelity and very low latency. For sure, you need a robust Bluetooth solution. And in this context, RF coexistence is challenging to achieve due to the small antennas and the proximity to the body. And all of this must be achieved with tight cost, size, and yield constraints. Every cubic millimeter count, and various design and manufacturing strategy exist, including single versus dual die for the Bluetooth audio solution, which is what we are going to discuss in the next few slides. So if you start today the design of a Bluetooth audio chip, one important question is which Bluetooth technology to integrate in the product. So first thing is that the market still requires Bluetooth Classic support for backward compatibility. Actually, today, most of us use the A2DP profile for music streaming and HFP profile for phone call. They are based on Bluetooth Classic technology, actually, the legacy Bluetooth technology. There is a huge install base of devices supporting these and not yet supporting LE audio. So that's why you need to support Bluetooth Classic. LE audio is gaining traction for its low power benefits and also for new use cases that it supports, like Auracast, which is an audio broadcast mode allowing unlimited number of audio peripherals to listen to the same audio source. This is particularly attractive for assistive listening and in public locations such as airport, bar, cinema, etc. Higher data throughput is getting mandatory also to support high resolution multi-channel music streaming. And this is why for new design start, it's essential to support the next generation of Bluetooth that will support higher data throughput up to 7.5 megabit per second. That is expected to reach the market in somewhere between 2027 or 2028. Channel sounding with its advanced ranging capability is also becoming essential, not only for the Find My Device application, but also for other interesting use cases, such as automatic left-right identification for the speakers, or a home theater system with automatic audio balancing. So if we look at the power profile of a typical TWS product, it is interesting to note that the radio, meaning the Bluetooth solution in this case, so the radio, the analog codec, including ADC and DAC, and DSP computing, each of them consume roughly 30% of the total power budget. So this highlights why tight integration and efficiency across the radio, the DSP, and the codec, and for sure the power management, are absolutely critical to improving the battery life.
Traditionally, audio chips are made of a monolithic die. You can see in the diagram in the right that you have your mixed-signal IP in green and your digital IP in blue, and everything is included into a single die. This approach brings some pros and cons, especially in 40 and 22 nanometers, where the cons are that mixed-signal IPs are cost and yield optimized for this process. Also, it's a mature process. These are mature processes, and so the IPs are widely available into different IP vendors and are robust and silicon proven. The drawbacks are that for advanced feature that is more and more demanded, like ANC, active noise cancellation, voice command, scent detection, spatial audio, head tracking, edge AI, the computing power is more and more demanding. And bigger software means bigger memory and die size, and higher DSP computing means higher power consumption. To help you compare, we have here a table with the process node and the relative density of the node compared to the 22 nanometers. So for example, between 40 and 22 nanometers, the relative density is 0.46 times the density of 22. You also have the estimated wafer price. So for 40 nanometers, it's more or less 30% less than 22. Another option is to split your audio chip into two different die, the mixed signal one and the digital one. This approach will bring you more flexibility on the computing side of your chip. The digital die can be in much more advanced nodes, such as 5 or 3 nanometers, that will offer higher density and more computing power. The analog die can stay in more mature nodes, such as 22 nanometers, where it will be optimized and where you can find a large ecosystem of different IPs. Both die can hence be optimized in terms of PPA. The dual die partitioning will also bring you flexibility, and you can make it a platform by having an analog die or mixed signal die that you will keep in your system, and then modifying the digital die for your evolution of the product. The drawbacks of this method are the higher cost. Having two dies is a bit more costly. It's a bit more complex in terms of design and verification. The supply chain is also different. You will have multiple wafers, and you will touch advanced packaging limits.
So thanks, Etienne. Please let me jump in here. So here is an alternative dual die partitioning to further illustrate the trade-off. In this approach, the die 1 not only integrates the PMU, analog, and radio, but also all the necessary hardware accelerator, CPU, and memory for the low-level Bluetooth functionality. This partitioning brings additional flexibility where the Bluetooth die and the application processor die can follow independently their own life cycle. It also enables easy differentiation, combining the Bluetooth die with various application processors dies. So we have seen that the old geometry single die architecture has some limits. It particularly constrains the innovation where feature set and processing power capability come at significant extra cost, if not restricted. The dual die architecture brings flexibility, but adds manufacturing complexity and challenges. So the key question becomes, can we combine simplicity and cost efficiency of monolithic designs with the performance and scalability of advanced nodes? That's exactly the problem we set out to solve.
This is a very good question you're asking here. And I believe that the 12 nanometer monolithic approach could be a solution. In fact, it combines the simplicity of a monolithic approach and the balance between high density and analog constraints. You can have both your analog and digital parts in 12, having an analog part that is not as optimized as in 22, but a digital part that will be much better than in 22 nanometers. Depending on your application, if you need this computing power for AI, for example, or any other application with ANC or high demands in the computing side, that can be a very good solution. The single die, it's smaller and lower cost in terms of packaging than dual die, and it optimized for power and thermal efficiency. The drawbacks of this solution is that it will be harder to find IP providers in 12 nanometers. We can look again at the table comparing the relative density and the wafer price, and we see that in 12 nanometers, the relative density is 1.84 times the one of the 22 nanometers, and the wafer price is 35% higher.
So here is an illustration of a monolithic Bluetooth audio solution in TSMC 12 nanometer. So this is where the Ceva and Dolphin collaboration comes in by combining Ceva's wireless DSP and AI IP with Dolphin's high-performance audio ADC DAC and power management. We enable a true 12 nanometer single die Smart Edge AIoT SoC for earbuds, headsets, smartwatches, and smart glasses. Ceva brings the Lynx 200 turnkey fully integrated IP platform comprising a controller, modem, and RF supporting next generation Bluetooth HDT and IEEE 802.15.4 for Zigbee, Thread, and Matter, powered by a RISC-V processor to execute the software protocol stacks. This platform accelerates time to market. It simplifies integration into MCU platform that runs the host protocol stacks and application, also combining DSPs and NPU, such as the Ceva Neutron Nano, to efficiently execute audio codecs, noise reduction, head tracking, spatial audio, voice command, tap detection, and other sensor fusion.
Dolphin Semiconductor has developed in 12 nanometer a very low power ADC, a DAC with a Class D architecture to have the best efficiency for high-end products, and an oscillator. These products have been tested on silicon. To summarize this presentation, we have seen that the TWS and OWS market is really growing, and there is a rise in the adoption of new form factors such as smart glasses in audio. These new use cases, allowing the different players to differentiate, also come with different challenges. We have seen the tiny form factor, the battery life, the audio fidelity, the low latency ANC and AEC, and the robust Bluetooth connectivity.
So traditional single die and dual die approaches each have limitations. Moving to 12 nanometer monolithic solution provides a good balance actually. And a fully integrated TSMC 12 nanometer monolithic architecture comprising Bluetooth, audio, power management, and AI IPs provides an optimal path forward for next generation Bluetooth device. So in this context, Ceva and Dolphin Semiconductor are the only IP partners to enable your next SoC. Thank you for your attention. So we hope you appreciated this webinar. You can find more information for sure on our websites.